Good morning, ladies and gentlemen. This video is going to be rotation 1 of the 3 rotations. If you have not yet done the other 2, you'll be doing labs investigating and proving the law of conservation of momentum. During this station, you will both take some notes on the law of conservation of momentum as well as do some practice problems. We're going to start by reading from your text. You should have received a copy of that text reading. And I'm going to go ahead and read it with you. Right now we're looking at 8.4 Law of Conservation of Momentum. You can follow along both on the screen and on the text. 8.4 Conservation of Momentum. I'm going to start by looking over here. Teacher Howie Brand shows the black couples, meaning falls. When the swinging dart, this thing is on some sort of strings here, bounces from it. So this thing came and bounced and now it's bouncing back. And he removes the rubber head of the dart so it doesn't bounce, it hits the black. Oh, you know what? This is about the section earlier, and I know that because it's about bouncing. So we're going to actually ignore that. I'm showing you that because it is important to look at your diagrams first, but sometimes your diagrams go with them. All right. From Newton's second law, x force equals mass times acceleration, you know that to accelerate an object, a net force must be applied to it. This chapter says much the same thing, but in different language. If you wish to change the momentum of an object, as mass times speed, exert an impulse on it. So put an impulse on it. In either case, the force or impulse must be exerted on the object by something outside the object. This goes back to our systems. Internal forces don't work. For example, the molecular forces within a basketball have no effect on the momentum of the basketball. Just as a push against the dashboard of a car you're sitting in does not affect the momentum of the car. Molecular forces within the basketball and a push on the dashboard are internal forces. They come in balanced pairs that cancel within the object. To change the momentum of the basketball or the car, an outside push or pull is required. If no outside force is present, no change in momentum is possible. So this seems important. No outside force is present, no change in momentum is possible. I'm going to flip to the next page. We still haven't talked about conservation yet, so I'm assuming we're going to get to that here. Oh, here's little mouse. Most of the cannonball's momentum is in speed. Most of the recoiling cannon's momentum is in mass. Little mass, big V, big mass, little v. Okay, that's about this. The momentum before firing is 0. After firing, the net momentum is still 0. Because the momentum of the cannon is equal and opposite to the momentum of the cannonball. Oh, so the P's are equal but opposite. Equals amounts, opposite directions. Consider the cannon being fired in figure 8.10. The force on the cannonball inside the cannon barrel is equal and opposite to the force causing the cannon to recoil. That means bounce backwards or move backwards. Recall Newton's third law about action and reaction forces. These forces are internal, inside. These forces are inside the system, comprising, making up the cannon and the cannonball. So they're inside the system of the cannon and the cannonball. So they don't change the momentum of the cannonball system. Before the firing, the system is at rest and the momentum is 0. After the firing, the net momentum, or the total momentum, just like net force, is still 0. Net momentum is neither gained nor lost. Okay, so just like my forces canceled out, the momentums, because they're equal and opposite, cancel out. Net momentum is neither gained nor lost. Let's consider the effects of internal and external forces carefully. Momentum, like the qualities velocity and force, has both direction and magnitude. That's size or amount. It is a vector quantity. Like velocity and force, momentum can be canceled. So although the cannonball in the preceding example gains momentum when fired, When the recoiling cannon gains momentum in the opposite direction, the cannonball system gains none. The momenta, plural form of momentum, of the cannonball and the cannon are equal in magnitude, equal in size, and opposite in direction. Therefore, these momenta cancel each other out for the system as a whole. So they're equal in size, just like opposite forces cancel, opposite momentum cancel. No external forces acted on the system before or during firing. Since no net force acts on the system, there is no net impulse on the system, and there is no net change in the momentum. In every case, the momentum of a system cannot change unless it is acted on by external forces. A system will have the same momentum before some internal interaction as it has after the interaction occurs. When momentum, or any quantity in physics, does not change, we say that is conserved. The law of conservation of momentum describes the momentum of a system. The law of conservation of momentum says that in the absence of an external force, when there's not an external force, the momentum of the system remains unchanged. If a system undergoes changes wherein all forces are internal, as for example in atomic nuclei undergoing radioactive decay, cars gliding, or stars exploding, the net momentum of the system before and after the event is the same. So this is like the big deal right here. If there's no external forces, the momentum of a system remains unchanged. So at this point, I'd like you to take out your notebook. We're going to take a little bit of notes. So you should start these notes immediately after where you had your notes in the last unit. So the change in momentum. So remember first, or this unit, excuse me. Impulse, remember, is a force applied over time and it changes an object's motion, momentum. It hardly ever is going to change an object's mass. For our purposes, impulses are only going to change the speed. And force has to be from outside the system. I'm going to skip to the next slide or move to the next slide, but if you need to finish taking these notes, please pause the video at this point. The law of conservation of momentum is, here's the definition of it, total momentum of a system does not change unless an outside force acts on it. That's what we just read. And our example of this from the text was the cannon shoots the cannonball. The forces are from inside the system. The cannon's mass times the cannon's velocity plus the cannonball's mass times the cannonball's velocity equals 0. Now, how is that true? Because the cannonball's velocity and the cannon's velocity are opposite in direction, so one of those is going to be a negative number. Now, I know some of you are just learning about negative numbers, but this is really important that because they're in different directions, one of them has to be negative, which is what that says. Again, at this point, pause the video until you're done with these notes. Momentum, conservation, and collision. So collisions, there shouldn't be apostrophe there, so get rid of that. But momentum, conservation, and collisions. Here's 3 examples. And these are all things that can happen. If you've ever played pool or billiards, you can imagine these balls as pool balls. So when objects collide or run into each other, the net momentum of both objects before the collision equals the net momentum of both objects after the collision. So in our example, 2 pool balls hit each other and the total momentum doesn't change. So you do not have to write this down. Do not have to write this down, but I do want you to look through it with me. So we've got the red ball has velocity that's indicated by its purple arrow here, moving this way. It runs into the white ball. Now the white ball was stopped because there is no purple velocity. And now the red ball stops and the white ball moves with the same speed. So 2 balls collide head on, meaning hit each other right on. So their velocities are equal but opposite. And if you look now, the velocities are the same, except they're just moving in opposite directions. And the last one, if the 2 balls are moving in the same direction, what can happen is some of the momentum from the red ball, which was going faster, gets passed to the white ball. Some of the momentum from the red ball gets passed to the white ball. And now if you look, you can tell by the larger arrow here, the white ball is moving faster. So the total momentum here doesn't change, but they can move from one ball to another, which if you remember what the word conserve means, the total has to stay the same, but it can move from one object to another. You do not have to write this down. But if we were to put some numbers on this, say that if the masses are the same, and the red ball was moving at 1 meter per second. After the crash, the white ball would be moving at 1 meter per second. In the second one, their velocities are equal but opposite, indicated by this negative. So again, the total momentum is not changing. And the last one, it's just the red passes off some of its momentum to the white. Again, do not have to write this down. If you really want to, you can, but it's going to take you extra time, and I don't think it's necessary. Another thing you can know is that we can figure out is if two objects stick together, their new velocity is going to be the original velocity added up, so 4 plus 0, and divided by the total number of objects. So we've got two train cars. They're often used as an example because they travel in straight lines on railroad tracks. Two train cars, we're assuming that they have the same mass. We can add 4 plus 0, we get 0, and divide it by the number of objects, two train cars, so 4 divided by 2, gives us a final velocity of 2 meters per second. And also, here's another way to write this. This is going to be on your worksheet. You don't have to write this down. So at this point, if you didn't finish any of those notes, please pause the video and go back and finish those notes. I'm going to go on to the problems. All right, so at this point, make sure your name is on this worksheet. This is one of your assessment list items. And I'm just going to go through some of these ideas with you right now. The key here is that, remember that P stands for momentum. Let's look at this. Momentum before and momentum after have to stay the same. And that's going to be the biggest thing. If you can remember that, you're going to be on the right track. All right. So looking at number 1, I'm going to adjust there we go. So when these two freight cars, that's like, again, we're looking at train cars here, of different mass collide, run into each other, and couple, stick to one another. So crash and stick together. What will be their resultant velocity? So what's the ending velocity? Now what I've done is I've given you some steps to help you think through this for some of the earlier questions. So what is the moving cars? So I look at the picture. So this is the moving car. Initial, starting, momentum. So momentum, P equals M times V. That's my equation I need to use. I can list out P. I don't know what that is. That's what I'm looking for. M equals the mass is, we're going to use tons, even though that's technically a weight. That'll do for our purposes. And velocity was 4 meters per second. So I'm going to plug it in. Plug in 10 tons. For mass times 4 meters per second. And I get 40. Now what am I doing for a unit? Oh, it says write the momentum with the unit tons times meters per second. 40 tons meters per second. Sorry, I ran out of space there. What is the mass once they're stuck together? Okay, well, I'm just gonna, these two are getting stuck together, so it's just their total mass. And whenever we hear the word total, we know we have to add. 30 plus 10 is 40 tons. Now, what's their final speed? So let's list what we know. We know that at the end, the momentum is the same as the momentum was 40 tons, tons meters per second. We also know that their mass is 40 tons. We're looking for speed, which we represent with v, so I'm going to put a question mark there. Now, which equation do we need to use? Well, we need to use the one that has velocity, momentum, and mass. V equals P divided by M. V equals 40 tons, not tons meters per second divided by 40 tons. So 40 cancels out and leaves us 1. Tons cancels out and leaves us meters per second. So the final speed is 1 meter per second. And I'm going to circle that. Now I'll go back to the question. When these two freight cars of different mass collide, stick together, crash and stick together, what will be their resultant velocity? That's the answer. And does this make sense? Well, something that's smaller and moving at 4 meters per second crashes into something that's bigger, and they, in the end, they're moving 1 meters per second. Yeah, they would be going slower because they have more mass, and so they have less velocity. I want you to stop what you're doing, and I want you to stop the video, excuse me, and I want you to try number 2. I'm going to show you number 2 in just a moment. All right. If you didn't get 1 meter per second, please take a moment and look over my work. Is there something that you don't understand? If you got stuck on something, please talk to your partner and figure that out. Now, number 3 is different, so we're going to go through this one together. A football player runs at 8 meters per second and plows, meaning he runs into a 80-kilogram referee standing on the field, causing the referee to fly forward at 5 meters per second. Now he's standing, so I'm going to assume that his initial velocity is meters per second. If this was a perfectly elastic collision, meaning the football player stops and the ref moves, what would the mass of the football player be? All right, so we got quite a few steps. So this one's going to kind of work backwards. So we are given enough to find the we need to find the mass of the football player. So we're going to start with the momentum of the referee because we know that the referee's momentum he got from the football player. So what do we know? PMV. We know that we're looking for the ref's momentum, so it's probably not here. But 80 kilograms has to do with referee, so that's his mass. The speed, he moves at 5 meters per second. And we're looking for P. So P equals M times V. I'm going to plug in 80 kilograms times 5 meters per second, which gives me 80 times 5, 0, 400, 400 kilogram meters per second. Sorry that I didn't leave myself enough space. So this must have been the momentum of the football player. So we know that the football player stops because it says here the football player stops. So he no longer has momentum. So he gave all of his momentum to the referee. So the momentum of the football player was 400 kilograms before he started moving. So now we're looking for the mass of the football player. So we're going to put an M question mark. P equals, this is again his momentum before, but we can use his speed before to help us figure out that. And his speed before was 8 meters per second. So we got to go back. Let's look at our equations. Each one gives us mass. Mass equals momentum divided by speed. Mass equals momentum divided by speed. 400 kilograms per second divided by 8 meters per second. 400 kilograms divided by 8. Mass equals, well, I know that 8 times 5 is 40, so we'll just put a 0 on the end of that and I get 50 kilograms. Now, the last thing I want to do is double check. Does this make sense? Well, the mass of the football player is less than the mass of the ref. So, and the ref was moving after the crash at 5 meters per second. Before the crash, the football player is moving at 8 meters per second. So yes, that just does make sense because if something has less mass, it's going to have more speed if they have the same momentum. All right. I'm going to have you work on this now yourself. I am going to put a key up that you can utilize, but you have to be able to do this. So if you don't understand, make sure that you get help from either myself or from those around you. Good luck. Let me know what you need. Thanks.